Good morning, students. Let us start the class for today. Colpitt's oscillator was being discussed in the previous sessions, and Colpitt's oscillator comes under the tuned oscillator circuits. So you can see the circuit diagrams. The feedback circuit is made up of purely reactive elements like inductances and capacitances. When we use two capacitances and one inductance, we call it as Colpitt's oscillator. And when we use two inductances with one capacitance, we will call it as Hartley oscillator. And in the last class, I had told you how to remember these two oscillators in that way. If there are two capacitors, CC corresponds to Colpitt's. If there are two inductors, LL, and the unit for inductors is Henry, that way you can remember it as Hartley oscillator. So we had discussed the basic principles in the last class. Today we will see the next points in the same Colpitt's oscillator, that is called coupling. Now you can see there are two coupling types shown here called capacitive coupling and link coupling. You can see this capacitor C3. And in the last class I had told you that when the inductor passes DC, inductor should not be directly connected to the base because there will be VCC by 2 here. At the collector of the transistor, let me write it down. At the collector, you will have VCC by 2. So at the collector, when you have VCC by 2, that VCC by 2, it is ideal. That should not come here at the base. It will affect the quiescent region operation of the transistor itself. That is why we require this capacitor. Okay, let me change it to pen tool only. So we need this capacitor. We need this capacitor, and the output frequency, output AC frequency is coupled back to the input by means of this C3. So this is now capacitive coupling. Why we cannot directly couple? See, directly connecting the load to the output lowers the Q. Now we have this RL, right? Again we have one more coupling capacitor here, C4. Now you can see load is connected to the output by means of this capacitor. If at all we directly connect the load to the output, now that VCC by 2 will be across this RL. Now let me stop this. C3 is highlighting because it is for input coupling or feedback coupling. Now discussing the output coupling. If at all this C4 is shorted, then the VCC by 2 will be across RL. That is unnecessary wastage of DC current. That is one thing. Second thing is, when the load is directly connected to the collector, we have already seen the Q factor in the previous class, where Q factor is, or quality factor is defined as resonant frequency divided by bandwidth. Now if bandwidth is narrow, Q factor will be larger. Or if the resonant frequency is larger, then also Q factor is larger, but the point is resonant frequency is the required frequency for the given application. So the only way to increase the Q factor is to have a reduced bandwidth. In order to have a reduced bandwidth, it is always advisable to have a high level tuning circuit. The tuning circuit's efficiency must be much better. Now if we connect this RL in parallel with the L, you can see here, let us say this C4 is shorted. Imagine this way. There is no capacitance at the output. Now the load resistance in parallel with the output, and there is an inductance also there. Now because of these parallel combinations, you can see that along with the C1, RL is connected in parallel, right? even though inductance is connected back to the input, you can see as if the C1 and RL are in parallel. That means at the output, we are giving rise to an RC circuit which is in parallel. It is going to affect the tuning operation of the feedback circuit. So, best thing is isolate the load from the collector by means of an isolation component, and that is now this C4, that is capacitive coupling. So directly connecting the load to the output lowers the Q and hence may not initiate the oscillation process itself. If the output is loaded in the beginning itself, as soon as you switch on the circuit may not work like oscillator at all. Now, that is why we have this capacitive coupling. We can have one more method of coupling here at the right side. You can see it is an inductive coupling now. It is also called as link coupling. It can also be called as inductive coupling because we have an inductor from the output back to the input as the feedback. Now we are using it like a transformer. You can see there is a other inductance coil connected to this particular coil. Now whatever is the feedback that is going back to the input, part of it is coupled to the output directly through this transformer and load is connected to the output, which means here also there is an isolation of DC. Just like we had C4 in the previous circuit for isolating DC, here also we have an isolation of DC in the sense this is now a electromagnetic coupling. So this is called as link coupling, means two inductors are connected. Now while coupling, we should take care that the coupling should not lower the Q of the tank circuit as well. Now this tank circuit has got its own Q, right? Basically Q is what? FR divided by bandwidth. FR is dependent on the tank circuit itself. I had told you why is it called as tank circuit? Because it is storing energy. Capacitor is storing electrostatic energy and inductor is storing electromagnetic energy. That is why it is called as tank circuit. Now the coupling should not lower the Q of the tank circuit as well. That is when we choose the value of this C4 or when we choose the value of this transformer, we will have to carefully design the circuit in such a way that the tank circuit performance also is not affected. So these are the basics of coupling the load to the output. Let me proceed now. We have been discussing the common emitter configuration for the design of oscillators. Till now we have been discussing only common emitter. Now in the next slide, let us see, do we have any other option? You can see this particular oscillator which is having common base configuration. You can see here output is fed back to emitter, not to the base, and through the emitter it is going back to the output. Now you may think this is like we are feeding back to the emitter and we have a PN junction at the base to emitter, and will it work that way? It will work that way because we are working with the AC domain, not in the DC domain. We are not supplying DC current back to emitter. We are supplying AC signal back to emitter. By means of this, again the feedback network C1 and C2. I'm sorry. Now I am. Through this capacitive divider network of C1 and C2, we are feeding part of the output signal back to the emitter. And why we have C4 here? You can see this is a link coupling again, where you can see the inductance is connected to ground, which means the feedback circuit, actually this emitter is connected to ground through RE, right? So you can visualize the feedback network this way. That means through C1, part of the signal is going back to the emitter, and C1, C2L form the part of feedback circuit, and RL is connected by means of a link coupling or by means of a transformer, and C4 is present here to provide a DC isolation to the inductor. That way, this is also a Colpitt's oscillator where we are using two capacitors and one inductor. Now, when we feed this way, because of the change in the connection of the feedback, let me write it here. From the output, it is going back to input. So, let us say I have input here. Let us say I have input here, then I have output here. I am just showing you the emitter and base, emitter and collector. Now from the output, there is one C1 back to input. This is now that C1. Now from the output, there is one inductance to ground. And from the input, there is one capacitance to ground. Okay. Now you may think we were supposed to be having two capacitors separately and one inductor in between them. That was the normal configuration which we saw in the previous circuit. So you may think, is it not a different circuit as far as the feedback is concerned? I should say no. Why? Reason is emitter is connected to ground, AC ground is there. From the emitter there is an AC ground. Even though this RE is there for biasing, emitter is connected to ground also by means of this C2. So as far as AC is concerned, emitter is grounded. Okay. So you can see that output is coming back to emitter in the AC fashion because of the C2 itself. So you can visualize this loop this way. That way we should say, as C1 is also connected to the emitter, it is going to work like an oscillator only. Even though the feedback arrangement is slightly different, it is going to work like a Colpitt's oscillator only. And the formula is going to be the same. The only advantage is that with this particular circuit, we can have larger output frequencies when compared to the previous common emitter configuration. That is the idea here. You know that common base configuration generally provides very high output impedance. When it provides very high output impedance, we can have higher output frequencies in this particular circuitry. That is the idea. So now let me stop annotating here, and now you can see output is fed back to input, and the base is common to both collector and emitter. It is common to both output and input. And even at the base we have this C3, because any stray noises or stray AC should not be affecting our quiescent point. That is why from the base to the ground we have connected a capacitance. Now this is the common base configuration. I will not go into the much larger detail here because this is only for a theoretical importance. So now because of this common base configuration, we will be able to get a higher output frequency. I will show you the formula now. Formula remains the same. Fr equals 1 over 2 pi square root of L into C equivalent square root of Q square by Q square plus 1. When Q is larger than 10, we can ignore the complete right hand side of that particular expression. And it can be Fr is equal to 1 over 2 pi square root of L into C equivalent, where C equivalent is nothing but C1 C2 divided by C1 plus C2, as these two capacitors are in series. Now the feedback factor is slightly different here. In our earlier case, the feedback factor beta was C1 by C2, and as we have the condition A beta equals 1, when beta equals C1 by C2, A will be equivalent to C2 by C1. That we had seen in the previous session. Now in this particular circuit, the feedback factor is C1 divided by C1 plus C2. So naturally, the voltage gain for the amplifier minimum should be 1 over beta, because A beta has to be equal to 1. So EAV minimum is 1 over beta. This is nothing but C1 plus C2 divided by C1. So let me proceed. Now how to construct a Colpitts oscillator using JFET and op-amp? Quite simpler now, because in case of JFET, always the input impedance is very high. Even in case of op-amp, the input impedance is very high. This we had discussed in the case of RC phase shift oscillator also. So we can directly have a fixed bias network, fixed bias JFET amplifier along with the RF choke. I told you already about the purpose of RF choke. So we can have this C2, C1 and L as part of the feedback network, which is the same as our common emitter configuration. And we can have the CC as the coupling capacitor to the output, so that DC is blocked and AC is passed back to the input. Formula remains the same, 1 over 2 pi root of L into C equivalent, where C equivalent is nothing but C1 C2 by C1 plus C2. Similarly with the op-amp, you can see with the op-amp also we can set this amplifier's gain itself as RF by RI. This is the inverting amplifier now. It is minus RF by RI is 100 by 10 is 10. So we have set the A as 10 and beta we have to set. A beta should be 1. So beta we have to set as 1 by 10. If beta is 0.1, if A is 10 here, now A beta is equivalent to 1 and the circuit is going to work like an oscillator. Now why we should set this gain as RF RI? The reason is op-amp will have a ideally infinite gain, or practically op-amp will have a gain of 1000 or 2000 or more sometimes. So naturally we should not have that much of gain. If we have that much of gain, I am talking about the closed loop, open loop gain of the op-amp. The open loop gain of the op-amp, if it is 1000, now the beta has to be 1 over 1000. Again, that value 1000 will not be fixed as such. It will be different from amplifier to amplifier that way whenever op-amp is manufactured. Again, because of the beta of the transistors. So it is not at all advisable to use operational amplifier in the open loop gain. Whenever we use op-amp in the open loop configuration, we use it as a comparator and not as an amplifier. Now what is comparator? I will not tell you now. It is an analog comparator which you will learn about it more in the future courses in the next semester, not now. Let me not discuss about the op-amp now. In the next semester you are anyhow going to study in more detail about the op-amp. So whenever we use op-amp in the open loop configuration, we use it as a comparator, not as an amplifier, because its open loop gain is really very high. So we have to use it as a closed loop circuit when we use it as an amplifier. That is the reason here it is configured as closed loop circuit with the feedback and as an inverting amplifier. So the gain of the amplifier is minus of RF by RI, that is 100 by 10 is 10. I have already told you. So that minus sign indicates it is producing 180 degree phase shift. Now the feedback circuit also is going to produce that 180 degree phase shift, and when the A beta equals 1 condition matches, then the circuit works like an oscillator. Okay, let me proceed. The formula remains the same for all these circuits as I have shown you earlier. Let me show you that formula once again, because in the next slide we have an exercise. So this is the formula. Remember this formula. Q is equal to FR by bandwidth, C equivalent is equal to C1 C2 by C1 plus C2, and beta is equal to C1 by C2, AV is equal to C2 by C1. Because A beta we have to match it at least equal to 1. If A is greater than 1 also no problem for us. A beta has to be minimum C2 by C1 that way. If it is more than that, no problem for us. So with this recap, let me give you an exercise now. You will have to solve it and you will have to tell me the answer within a few minutes. Given C1 is equal to 0.001 microfarad, C2 is equal to 0.01 microfarad, L is equal to 15 microhenry. This U is micro. What is the frequency of oscillation for Colpitt's oscillator? What is the feedback fraction? How much voltage gain does circuit need to start the oscillations? Can you quickly solve all these three? I have shown you the formula already. Quickly solve all these three and tell me the answer. Students are taking too much of time, or are you really working out? When you have the calculator at your hand, it does not take this much time. Okay, Sain is giving the answer. AV is 90.9 into 10 power minus 9. No, something wrong. Something wrong. Because beta is C1 by C2, right? Feedback factor is C1 by C2 in case of Colpitt's oscillator. We are discussing the common emitter Colpitt's oscillator here. So when beta is C1 by C2, EAV is nothing but 1 over beta, because A beta has to be equal to 1. So the value of beta is directly evident here. C1 by C2, 0.001 by 0.01. So it is 1 over 10. And gain is C2 by C1. That is 0.01 by 0.01, that is 10. Yes. The gain is 10. Gain minimum has to be 10. That is directly evident. You don't need a calculator also to do that calculation. Now my question is, what is the frequency of oscillation? Answer given is 4.3099. What is that? Is it the frequency of oscillation? Gain is 10, beta is 1 over 10, that is 0.1. Feedback fraction is 0.1. Obviously, gain is 10. Now, someone has to give me the answer for the frequency of oscillation. First, find out C1, C2 by C1 plus C2 and substitute in the formula 1 over 2 pi square root of L into C equivalent. Okay, the answer given here is 1.3 megahertz. Let me see whether it is correct. It is 1.36 megahertz to be accurate. 1 over 2 pi root of L into C equivalent. It is 1.36 megahertz. Yeah, one more student has given the answer 1.36 megahertz. That is correct. So, Colpitt's oscillator's resonance frequency is 1.36 megahertz, beta is 0.1 and voltage gain is 10. This is a very simple exercise and this part of the module here in module 4 is quite an easy module or easy topics in the sense we do not have a lot of mathematical calculations here. It is simply substitution into the formulae and then obtaining the answer. So, even in the test or even in the exam, you will find questions such as the block diagram description of oscillators and the circuit diagram descriptions of the oscillators and then simply the substitution of the given values into the formulae. That way you can score well and it is quite easy also as far as the oscillators topic is concerned. But in the same module, earlier we discussed about the negative feedback and even though it seems to be a little tougher, you will have to study more and you will have to work out. I am only mentioning the oscillator part is quite easier. That's all. Don't take it lightly that the complete module is also quite easier. Not that way. So let me proceed. Now coming to the next type called Hartley oscillator. You can see here that instead of two capacitors and one inductor, we have now two inductors and one capacitor. Let me write it in a slightly different way. You can see that capacitor is connected directly between input and output. You can see output is connected back to input by means of this C. And we have one inductor L2 at the input and L1 at the output. So this is now L2 and this is now L1 and this is now that C. Now this is similar to the Colpitt's oscillator. In the Colpitt's oscillator we had two capacitors there and we had one inductor there. Instead we have one capacitor here and two inductors here. Otherwise the connections are same type. Now we have this capacitance here also. As I have told you, we need a DC isolation between output and input. For that this capacitance is there. And here there is this capacitance here also. Now when we connect the output to the load, we should again go for either capacitive coupling or link coupling based on the choice. So this is the Hartley oscillator which is going to work in the same fashion as the Colpitt's oscillator. The only difference is the feedback circuit's arrangement is slightly different. And the formula is also the same, 1 over 2 pi root of L equivalent to C. Now L equivalent is nothing but L1 plus L2. Why? Because these inductors are in series now. Even though there is a ground there, with respect to output and input, they are in series now. When they are in series, L equivalent is equal to L1 plus L2. Otherwise, everything else is the same. So let me proceed. Now the same Hartley oscillator can be constructed using JFET. Again you can see one L connected to ground here, one more L connected to ground here, and one C connected back to the input. Of course, the textbook authors write the circuits in many different ways. But the point is, in whichever way I have been telling you, that is the easy way to write the circuit diagram. Whereas textbook authors will have their own styles of writing the circuit diagram. Now here also you can see from output back to input there is a capacitance, and from this end there is a inductor to ground, and there is one more inductor to ground. Only thing is he has mentioned the output side inductance as L2 and input side as L1, whereas in the circuit which you see on the left hand side, output side inductor is called as L1 and input side is called as L2. In fact, the left side circuit I have taken from the book Malvino, and the right side circuit I have taken from the book Boyle-Stad. That's all. The two authors have two different styles of writing the circuit diagram. I recommend the way in which I have been writing the circuit diagram. That itself is a better circuit diagram because you can easily understand there. Otherwise they are all one and the same. So even in the JFET circuit also you can see the RF choke, and this is a fixed bias amplifier which is used in the case of JFET. Now the formula, as I have told you, frequency of oscillations FR is equal to 1 over 2 pi into square root of C into L equivalent, where L equivalent is nothing but L1 plus L2 because they are in series. Now the feedback fraction in case of this particular oscillator, beta, is L2 by L1 considering the left side circuit. Don't get confused with the right side circuit now. This formula is with reference to the left side circuit. L2 by L1, just like we had the same fraction there in the previous Colpitt's oscillator. So therefore the minimum voltage gain AV is equal to L1 by L2, that is the reciprocal of beta. So this is the Hartley oscillator. I will not be working out any exercise on this because it is simply a substitution of the same given values. We already had an exercise with the Colpitt's oscillator. We don't have to have the similar exercise in the Hartley oscillator, but you will have to work out those exercises for your practice. Coming to the last oscillator, actually we are coming to the last part of this module now. Coming to the last oscillator, that is called crystal oscillator. We have been discussing initially the RC phase shift oscillator, which is used in the range of audio frequencies. That means in the range of, let us say, 5 Hz till around 100 kHz. Later on we discussed the Colpitt's and Hartley oscillators, which we can use for more than 100 kHz in the radio frequency. But the problem with those Hartley and Colpitt's oscillator is we are using again reactive components, and all these reactive components will have tolerances. Because of the tolerances, even though we design a Hartley oscillator for a very accurate frequency, when we connect those components, because of the component tolerances, we may not get the very accurate frequency. If at all we have to get a very accurate frequency, then we should go for minimum tolerant component values. That was the challenge there. And one more challenge there was, we are using the tuned circuit oscillators or tuned oscillators with the kilohertz range, whereas in some cases we require highly accurate frequency. There we go for usage of crystals. You have already studied about the quartz crystal in the engineering physics course, I suppose so, or you would have studied about the crystal even in your 11th or 12th standards or in the PUC course. I suppose you already are aware of crystal. Now, just to give you an example, we regularly use the clocks and the watches. Even on my hand now I have a wristwatch, and this watch is giving me 1 second time, that is its minimum resolution. 60 seconds 1 minute and 60 minutes 1 hour. That way the clock keeps showing the time. Now, what is there inside this wristwatch or inside the clock? which we use at home or anywhere for watching the time, there is a crystal here. Let me tell you, as far as our wristwatch is concerned, we have a crystal called 32 kilohertz crystal. It's a quartz crystal. And by the fundamentals of your physics, you already know that quartz crystal works under this piezoelectric effect. Piezoelectric effect means whenever a voltage is applied across the crystal has a insulator inside. This quartz is basically an allotrope of silicon dioxide. Quartz is basically SiO2. It is an allotrope of sand basically. For that matter, all stones are, when they crush down, they will become sand only, right? All those stones, most of the stones. And sand, when it is crystallized, that is also small stone piece only that way. So stone or silicon dioxide or sand, they are all insulators. They don't conduct current. Now quartz is an allotrope of silicon dioxide, it's an insulator. Now you already know, when we put an insulator in between two conducting plates, current cannot flow, right? Current cannot flow, but current tries to flow because there is an electromotive force. When current tries to flow, the small quartz piece which is in between, it is subjected to the electrical pressure. Imagine we are applying an voltage across this quartz crystal. When you apply a voltage is a electromotive force. So because of the voltage, electrons tries to move from minus to plus because electrons are negatively charged. When electrons try to move, there is an insulator in between the two plates. So this works like a capacitor now, where electrons cannot move to the other side. But electrons induce, for example, electrons which are at the negative plate, they will induce holes at the positive plate. Okay, because at the positive plate, electrons repel electrons, so electrons go away from the positive plate, and when electrons go away from the positive plate because of the repulsion of electrons only, then the upper plate becomes positively charged. But what happens to the crystal now? When there is this electrical pressure inside, that quartz crystal is a very thin material, that thin material vibrates now. When it vibrates, the crystal has got a natural frequency of vibration. As such, I have been telling you, when you play guitar or sitar or veena, the string will have its own frequency of vibration. It depends on the thickness of the particular string. Thinner string will vibrate with the larger frequency, and the thicker string will vibrate with the lesser frequency because of the inertia basically. Now, we can say that each string in the guitar or sitar or veena has got a natural frequency of vibration. For that matter, even my vocal cord has got a natural frequency of vibration. Your vocal cords also have got a natural frequency of vibration. All of our voices are different, right? We can recognize a person just by listening to the voice frequency itself, right? Because everyone's voice frequency is different. Only with the mimicry artists, they modulate their vocal cords in such a way to imitate somebody's voices. Otherwise, even the mimicry artist's voice frequency is also different. So, all of us have the vocal cords which are manufactured or designed by God with the different sizes. So naturally, the vocal cord is a very complicated apparatus in our human body, which is situated in the throat region. And when we want to speak, our thought force goes all the way to the vocal cord. Through the nervous system, the vocal cord vibrates. When the vocal cord vibrates, we are expelling the air from the lungs. Air comes out of the lungs, and when it hits the vocal cords, when they vibrate, they produce the sound or the voice. That is how right now you are listening to me. So that way, each person's voice frequency is different. Let me tell you a small Samskrita Subhashita here. Pinde pinde matir bhinnaha kunde kunde navam payaha jatav jatav navacharaha navavani mukhe mukhe. This is a beautiful Subhashita which says, Pinde pinde matir bhinnaha. Head to head intelligence is different. Kunde kunde navam payaha. Pond to pond, the taste of water is different. Jatav jatav navacharaha. Caste to caste, the lifestyle and the culture is different. Navavani mukhe mukhe means person to person or mouth to mouth or throat to throat. The speech quality is different. This has been told many centuries before, maybe with some Sanskrit poets. So this indicates each person's voice frequency is different. Now that is what we call it as natural frequency. In that also, male frequency range is different, female frequency range is different, children's frequency range is different. Male frequency is around 300 to 600 hertz, female frequency is around 600 to 900 hertz, and children's frequency is from 900 to 1200 hertz. Again, that depends on the size of the vocal cords. Males undergo puberty during adolescence, due to which the vocal cords become thicker at that time. This is the nature's way of self-defense by means of a harsh voice in case of males. Because in the prehistoric ages, males used to go out searching for food, where females used to stay inside the caves taking care of the children. So females will not have that harsh voice or hoarse voice because their vocal cords do not undergo that physiological change. But with males, this undergoes a physiological change, due to which male voice is different from female voice. And children's voice is of a higher frequency because children's vocal cord is still thinner. So let me come back from biology to electronics now. I was telling you all those examples only for you to understand what is meant by natural frequency. Now this quartz crystal will have a natural frequency, but this is dependent on the size. This 32 kilohertz is proportional to the size, or I should say it is inversely proportional to the size. Let me write 1 hour here. The frequency of oscillation of the crystal is inversely proportional to its size. Thinner the crystal, larger the frequency. Thicker the crystal, lesser the frequency. So the point here is, whenever we apply an electrical voltage or electrical pressure, basically the crystal is nothing but a capacitor where there is an insulator inside. But in the case of our regular capacitors, we are using ceramic or rubber or paper as insulator in between. In this case of electrolytic capacitor, it is paper impregnated with the electrolyte and made as a foil inside a rubber, so as to have a larger capacity of storage. In the case of ceramic capacitance, it was a ceramic plate inside. They do not have a piezoelectric effect here. They do not have a piezoelectric effect. But the quartz is going to have this piezoelectric effect, where when we apply electrical voltage, the quartz vibrates with its natural frequency. And the natural frequency is 32 kilohertz. So now, what is done in the case of our wristwatches is, this 32 kilohertz which is coming out of the crystal, that crystal is connected as a feedback element to the amplifier now. Our feedback circuit will be crystal only now. Crystal is connected as a feedback element to the amplifier, and the amplifier's output is now 32 kilohertz. This is given to a divider. It is given to a divider. Now the divider's coefficient is 32. So output you will get it as 1 hertz now. That 1 hertz is nothing but 1 second now. So inside our wristwatches or our clocks at homes or at offices, we have this 32 kilohertz crystal inside, and output of that oscillator is given to a digital circuit now, or a logic circuit, which is a divider. Just like multipliers, you have dividers now. So through the divider now, it is divided by 32, and the output of the divider is now 1 hertz. Sorry, I have to admit a student. Okay. Output of the divider is now 1 hertz. That 1 hertz is now 1 second. That 1 hertz pulse is shown either on the LCD display or it is given through some other electromechanical arrangement to the needle which is moving in seconds. So that is how our regular wristwatch is going to display the time. So I gave you some basics of crystal oscillator today. In the next class,